Hello everyone. Welcome to the class of Discrete Mathematical Structures. Today, I'll be teaching a topic in Module 1, Fundamentals of Logic, and the topic name is Open Statements with More Than One Variable. Myself, Dr. Madhura, Assistant Professor in the Department of Mathematics, Sai Vidya Institute of Technology, Bengaluru. Statements involving more than one variable. The open statements containing two variables x and y are usually denoted by p of x comma y, q of x comma y, etc. And in the same manner, open statements containing three free variables x, y, z are usually denoted by p of x comma y comma z and q of x comma y comma z, etc. So we are already familiar with the open statements which are of the form p of x, q of x, r of x, etc. Now we are dealing with two variables, three variables, etc. So open statements involving more than one variable we are now talking about. So they are represented symbolically in the form pxy, qxy, or with three variables it is pxyz, qxyz, etc. Universe can be same for all variables or different for different variables. So sometimes x belongs to some universe and y belongs to some other universe. Or sometimes both x comma y might belong to the same universe. Say for example, we have the open statement p of x comma y such that x minus 2y is a positive integer, which can be symbolically written as x minus 2y is greater than 0. Or another statement with three free variables x, y, z. P of x, y, z is another open statement such that x plus y minus z is equal to 0. So these are some of the examples for open statements which involves more than one variable. If U is the universe for X and V is the universe for Y in an open statement P of X comma Y, and suppose A is an element belonging to the universe U and B is another element belongs to the universe V, then the proposition got by replacing X by A and Y by B in the open statement P of X comma Y is usually denoted by P of A comma B. So we picked an element in the universe U and another element in the universe V. That is A and B are the elements what we picked from the two different universes. And U is the universe for X and we have taken B as the universe for Y in the open statement P of X comma Y. So the elements picked A and B belonging to different universe. Then the proposition obtained by replacing x by a and y by b is denoted by p of a comma b. The open statement with respect to the elements a and b. Next we have quantified statements with more than one variable. If p of x comma y is an open statement with variables x and y, we can have the quantified statements of the following form. So suppose we have the open statement in the form p of x comma y involving the variables, two variables x and y. Then the quantified statements can be symbolically in these forms. For every x, for every y, p of xy. For some x, for some y, p of x comma y. For every x, for some y, p of x comma y. And lastly, for some x, for every y, p of x comma y. So these are different quantified statements for us, symbolically represented for the open statement p of x comma y. If x and y have the same universe, then the expressions 1 and 2 can be written as for every x, for every y, p of xy is logically equivalent to writing for every x comma y, p of xy. Suppose we pick both x and y from the same universe. Then for every x, for every y can be clubbed together and written as for every x comma y, p of xy. Similarly, If both x and y are from the same universe, we can also write down for some x, for some y, p of xy can be clubbed together and written as for some x comma y, p of x comma y. So this is happening only when both x and y are coming from the same universe. Note, for every x, for every y, p of xy is always logically equivalent to writing for every y, for every x, p of xy. So if we reverse the variables x and y, it is still the same. The logical equivalence is same for both. For some x, for some y, p of xy is also logically equivalent to for some y, for some x, p of x comma y. So again here, x and y are reversed. So these are having the same truth values. So that is the reason they are logically equivalent to each other. So this is about open statements which involve more than one variable. So let us do some of the simple problems in this. Let us see problems now. Problems. First question. Prove that the following argument is valid. Prove that the following argument is valid where A and B are some particular members of the universe. Where A and B are some particular members of the universe. The given argument is for every x, for every y, p of x comma y, conditional q of x comma y, negation q of a comma b. Therefore, for some x, for some y, negation p of x comma y. So this is the given argument for us. We have to prove that the given argument is valid. Okay. We infer the rules of inferences. We recall it, and these are the premises given for us. For every x, for every y, p of xy conditional q of xy is one of the premises. Negation of q of a comma b is another premises. So we recall that we take and between the premises and we try to arrive at the given conclusion. If we arrive at the given conclusion, then the given argument is valid, otherwise it is invalid. Correct? So recalling the property from the rules of inferences, we will move ahead to the solution. We take and between the premises first. So for every x, for every y, p of x comma y, conditional q of x comma y, and negation q of a comma b, and negation q of a comma b. So this implies for us, since the first bracket is true for every x, for every y, I can apply it for a comma b also. So we will write it down as p of a comma b conditional q of a comma b, and negation q of a comma b I will write down as it is. Now, in view of the modus tollens, in view of the rule modus tollens, what we had learned previously, this is of the form P conditional Q and negation Q. P conditional Q and negation Q is logically equivalent to negation, or this implies, actually, instead of writing logically equivalent to, let us write down implies. Okay, this implies negation P for us. This is in view of the modus tollens. Modus tollens. So keeping this in mind, let us apply for the previous step what we had. We have in place of P, P of A comma B. We have in place of Q, Q of A comma B. So we have negation Q of A comma B. So this should imply negation P for us. So this is going to imply negation P of A comma B for us. Negation P of A comma B and application of modus tollens rule, right? So this can be in turn written as for some x, for some y, negation P of x comma y. For some x, for some y, this is negation P of x comma y, right? So we had it for every a comma b, this is being sat for every x comma y, this is being satisfying. But when it comes to the resultant, it is applicable for some elements x and y. That's because we are arriving at negation of p of a comma b, where a and b are some arbitrary members of the universe. So it might be for some x, for some y, being satisfying negation p of x comma y. So therefore we conclude given argument is valid. So we will be now able to understand that given argument is valid because we have arrived at the given conclusion, right? So this was the first question to you. So now we'll move on to the second problem. Find the negation of the following quantified statement. Find the negation of the following quantified statement. And the statement given for us is for every x, for some y, p of x comma y and q of x comma y, conditional r of x comma y. For every x, for some y, p of xy and q of xy, conditional r of x comma y. So we need to obtain the negation of this given quantified statement. So let us do the solution. Let us do the solution for the same. So we have the given quantified statement. I'll write down the negation outside for the same. So negation of for every x, for some y, for every x, for some y, p of xy, p of x comma y and q of x comma y, conditional r of xy. This is the given quantified statement for us, and I've written the negation outside for the same. Okay. Now we have to take negation of this entire expression, right? So when I take the negation of for every x, it becomes for some x. So we will do step by step. Okay, so first I will take for every x. So this is logically equivalent to writing for some x, negation of the entire remaining now, negation of the entire remaining, that is for some y, p of x comma y and q of x comma y, conditional r of x comma y. Right? So what did we do here? Negation of for every x. Negation of for every x can be written as for some x. For some x. And I've taken negation for the entire remaining expression and written as it is. As it is. Now this in turn is logically equivalent to for some x. What is negation of for some y? It becomes for every y. For every y, we have p of x comma y and q of x comma y, conditional r of x comma y. Conditional r of x comma y. And of course, we have to write down this negation for the entire thing. Negation is still to be applied for the compound proposition what we have here. So we have p of xy and q of xy, conditional r of x comma y. So if you observe, this is exactly of the form. We have a negation here, so don't forget that. Okay, so this is of the form negation of P conditional Q. Negation of P conditional Q, we remember that negation of P conditional Q is logically equivalent to P and negation Q. P and negation Q. This is one of the remark what we learned in the previous topics. So using this expression, using this formula, we can now arrive at this given expression is logically now equivalent to, or the negation of it is now equivalent to, for some x, for every y, p of x comma y and q of x comma y and I'll put a flower bracket for this, and negation r of x comma y. Negation r of x comma y, because we have to arrive at p and negation q. So whatever in place of the p was there, I wrote it as it is, and negation q. So negation r of x comma y we have to write down. So this is the negation of the given quantified statement. Third problem. Third one. Determine the truth value of determine the truth value of each of the following quantified statements comma given the universe is the set of all non-zero integers. Given the universe is the set of all non-zero integers. First question, for some x, for some y, x into y is equal to 1. Second one, for some x, for every y, x into y is equal to 1. Third one, for every x, for some y, x into y is equal to 1. Fourth one, for some x, for some y, 2x plus y is equal to 5 and x minus 3y is equal to minus 8. Fifth one, for some x, for some y, 3x minus y is equal to 17 and 2x plus 4y is equal to 3. Right, so we have to determine the truth value for each of these quantified statements, and given the universe is a set of all non-zero integers, we have to do it for all non-zero integers, and what is to be determined is nothing but the truth value. So truth value, so either the statement is true or the statement is false. We will mention that along with the valid reasons. Okay, so let us do the solution for one by one. For the first one, it is a valid statement or the statement is true because suppose we take any particular value. This is for some x, for some y. So for some x and y value, say x is equal to 1 and y is equal to 1. What will be the product x into y? So x into y is equal to 1 itself. The statement is valid for some values of x and y. For some values of x and y, the statement is true. So that is why we can conclude the given quantified statement. The first one is true. Second one, so it says that for some x for every y means for a specified value of x. So for a specified value of x and for every value of y, we have to show that xy is equal to 1. This is a false statement because for a specified value of x, x into y for every y need not be true. So suppose I take x is equal to 1. For every y, this is not true. When I take y equal to 1, x into y will be equal to 1. But when I take y equal to 2, and I've already fixed the value of x as 1, so 1 into 2 will be 2, which is not equal to 1. So the second one will give us a false. False. Because for a specified x, for a specified value of x, x into y is equal to 1. For every y is not true. For every y, this is not true. Okay. So this is what the reason behind it, why it is a false statement. Now let us see the third one. Third one is again false because it happens in the same manner for the second case what we did. For every x, so suppose I take x is equal to some value say 2, there is no integer y such that x into y is equal to 1. Remember the universe here is a set of all non-zero integers, right? So when I take a particular value of x, for every x they are telling, no? So suppose I fix the value of x as say 2. Then there is no integer y found such that x into y is equal to 1. So that is the reason behind the third one to be false. So I'll just put that in the next page. So we have third one, solution is false because for x is equal to a specific value say 2, there is no integer y such that x into y is equal to 1. Such that x into y is equal to 1. So that was the third one for us. Now we have fourth one. Fourth one, it says for some x, for some y, 2x plus y is equal to 5 and x minus 3y is equal to minus 8. So we have to find a value of x and y. For some values of x and y, this is satisfying or not. Okay, so let us check that. Say for x is equal to 1 and for some x, for some y. Say for x is equal to 1 and y is equal to say 3. So what happens to this result? And x is equal to 1, it becomes like solving these two simultaneous equations you can do and check it out. Okay, so for some x is equal to 1, we have 2x plus y is equal to 5 being satisfying, and for y is equal to 3 also this is being satisfied. 2 plus 3 is 5, x is 1, y is 3, so 1 minus 9 is minus 8. So for some values of x and y, this is and between these two, so true and true will give us true. Both has to be true, no? 2x plus y is equal to 5 has to satisfy, as well as x minus 3y is equal to minus 8 has to satisfy. So there's and between these two. So that is the reason you have to both for some values of x and y, particular value of x and y, whatever we take, it has to satisfy both these bracket terms. Okay, so this is finally giving me a true. True. That is because taking x is equal to 1 and y is equal to 3. When we take x is equal to 1 and y equal to 3, we see that it satisfies the equation and there is and between both the statements. So and between both the propositions also satisfy for this. So next one, we need to obtain in the same manner for some x, for some y. right? So let us check with any random values, taking x is equal to say 5 here. So 5 threes is 15, minus of minus 2. Suppose y is equal to 2 minus 2. So 5 and minus 2 is satisfying the first one. Whereas for the same set 5 and minus 2, if you observe, it is not satisfying the second equation, that is 2x plus 4y is equal to 3. So whatever the set of values that you take for x and y, it has to satisfy both these expressions because there is an and between it. So here we observe that the fifth one is a false statement because both these equations do not have a common integer solution. They do not have a common integer solution between them. For the same set of values of x and y, both these are not satisfying. So that is the reason fifth one is a false statement. So we will write on the solution with the reason false because the equations 3x minus y is equal to 17 and 2x plus 4y is equal to 3 do not have a common integer solution. They do not have a common integer solution, and that is the reason this is a false statement. So we observed and we obtained the solution for all the 5 different cases. The third one is false, fourth one is true, fifth one is also false. And we observed in the previous two cases, they are respectively true and false. Okay, so this is how we work problems based on open statements involving more than one variable. Hope these problems have given you the idea behind the topic. Thank you for watching.